Hi everyone, welcome to our last lecture on Chapter 5. This will conclude our talk about gases. So, all of the gas molecules in a sample of gas can travel at different speeds. Some, will travel a little bit faster, some will travel a little bit slower, but this distribution of speeds will follow a statistical pattern called a Boltzmann distribution. And this Boltzmann's distribution is kind of the shape of a curve like this, where some gas particles are moving a little bit slower, some are moving a little bit faster, but most of them are kind of falling in this general range here. So we'll talk about the average velocity of the molecules, but there are different ways to take this kind of average. The way that we're going to use the average here is our root mean square method, where the root mean square average velocity, or this value, this URMS, is the square root of the average of the sum of the squares of all the molecule velocities. And rather than doing all of that, we have a simple formula here. So we have our root mean square velocity is equal to the square root of 3RT over M. So R is a different value. So this is not the ideal gas law constant. This is more of a thermodynamic R value. And so we also have T, which needs to be in Kelvin. And then M is going to be our molar mass, which is going to be in grams per mole. Okay. So we can then, if we have the average velocity, we can then calculate the average kinetic energy of the gas molecules, because the average kinetic energy depends on the mass, which we can find, right, our average mass, and then now we have our average velocity, and so this average velocity we would use as the root mean square velocity. Gases in the same container will be at the same temperature, and by definition, that means that they have the same average kinetic energy. Okay, so this is a definition here. If we are at the same temperature, then we have the same average kinetic energy. That doesn't necessarily mean that, if you have two different gas samples, say we have like helium and nitrogen, and they're at the same temperature, they will have the same average kinetic energy by definition. But that doesn't mean that those gas particles are moving at the same velocity, because they will have different masses, they will have a different velocity, but they're going to be manipulated in such a way that it will still equal the same kinetic energy. Okay, so if we look at this here, right, kinetic energy equals 1/2 mv squared. To have the same kinetic energy, the heavier molecules must have a slower average speed. And this should make sense if we're thinking about this mathematically, right? If we have a larger mass, then we need to have a smaller velocity so that Ke stays constant. The same is also true, right? If we have a smaller mass, then we need to have a higher velocity so that Ke always stays constant. So they're at the same temperature, but they're going to have, they're at the same temperature, so they're going to have the same kinetic energy, but because they have a different mass, they will have a different velocity. Okay, so if we look at oxygen, right, oxygen has the highest mass on here, and so therefore it's going to have the lowest molecular speed. Right, it's going to be here, whereas hydrogen has the smallest mass and it's going to have the highest average speed. And if you'll look, the faster these molecules start moving, the more the Boltzmann distribution kind of spreads out. And this is always going to be true. So when we have things that are moving slowly, we're going to have slowly on average, we're going to have a fairly narrow Boltzmann distribution. But as we get these molecules moving faster and faster and faster, there tends to be more of a range of the speeds that they can have. So the Boltzmann distribution will kind of spread out. So some can still be moving really slowly, where some can now be moving really rapidly. Okay. As we increase the temperature, our average velocity increases. And again, if we think about Ke equals 1/2 mv squared, right? As we increase the temperature, we are increasing the kinetic energy. So if we're increasing the kinetic energy, we can't change the mass, right? So that means as we increase the kinetic energy, our velocity is going to go up. And as our velocity increases, like I was talking about on the last slide, this distribution function will spread out. and it will result in more molecules with faster speed. So we're still going to have some down here, right, that are moving slowly, but now we're going to have some that are moving more quickly. And this distribution as a whole gets wider and wider. Instead of when we are moving more slowly, it's fairly narrow because there are not, there's not as wide of a range of velocities that these molecules can travel at. So here's an example of how we might calculate the root mean square velocity of methane at 25 degrees Celsius. And again, remember that this R is not our ideal gas law constant R. This is our thermodynamic R. So we have our root mean square velocity is equal to 3 RT over M, and M is going to be our molar mass. So we have our equation here. Okay, so then we can go ahead and plug in our numbers. So we have 3, and then our thermodynamic gas law constant, and then times our temperature in Kelvin. So we're going to add 273. Make sure you're always changing this to Kelvin, and we'll get 298 Kelvin. And then that will be over the molar mass. And so our molar mass of methane is 16.05 grams per mole. And so when we, math this out, we're going to get that our root mean square velocity is equal to 21.5 meters per second. Okay, so pretty straightforward. I won't walk you through how we're getting to meters per second here, but I will have you just remember velocity is going to meters per second because we've got square roots of things and we need to do some equalities with the units. I would just go ahead and remember that our velocity is always going to be in meters per second. Okay, another topic that we talk about when we get to gases is this mean free path. And it sounds a little more complicated than it is. Essentially, what it is that molecules in a gas travel in straight lines until they collide with another molecule or the container, right? We've talked about that before. That's one of our kinetic molecular theories. So the average distance that a molecule travels between these collisions is called the mean free path. So it's essentially just how far it's going to go before it hits something. And the mean free path will decrease as the pressure increases. And this should make sense, right? If we increase the pressure, then we are usually making our container smaller, right? That's how we're getting that increase in pressure. Or the way that we're getting an increase in pressure is that we are adding more molecules to the same volume. Either way, whether we're adding more molecules or we're making the container smaller, we're increasing the frequency of the collisions, right? And so when we increase that frequency of collisions, we are essentially making the collisions happen, right, faster. And so the average distance between the collisions is going to get smaller, right? So our mean free path will decrease as pressure increases. And again, like I said, that can be due either to the volume decreasing or in us adding more molecules to the container. So 2 words that are kind of similar but different. We have diffusion and effusion. Likely you've talked about diffusion in biology because they tend to talk about it, things diffusing across, maybe a lipid bilayer or something like that. But we also have effusion, so they're slightly different. Diffusion is the process of a collection of molecules spreading out from an area of high concentration to low concentration. And so you can think about this like if I sprayed some perfume in the corner of our lecture hall. Then that would be a very high concentration of those particles, right, of that smell. And as time goes on, those particles will diffuse and spread out, right? The smell will travel because it's going to travel from an area of very high concentration to an area of low concentration. So that would be diffusion, going from high concentration to low concentration over time. Effusion is the process by which a collection of molecules escapes through a small hole. So that's going to be our key here, is that there is a small hole. And this says into a vacuum, or it could be into a very, an area of very low concentration, but it's escaping through a small hole. That's effusion. And so my favorite example of effusion is if you bought a helium balloon, right? And the helium balloon is maybe your helium is maybe held in a latex balloon or mylar or whatever the case may be. But that balloon has small holes in it. And over time, those helium particles can escape through the holes in your balloon, right? This is why over time our balloons get smaller and will fall to the ground. This is effusion. Over time, those helium particles are escaping through the small holes in the balloon into the rest of the atmosphere. Or you can think of an area of very low concentration of helium. Okay. This is what it would look like on a molecular level, right? So say, this could even be our balloon. And then we have like our holes in the balloon. And over time, every once in a while, one of those helium particles will escape, right? And over time, your balloon will get smaller and smaller and smaller, and it will fall to the ground. So this is a vacuum, presumably, or like I said, an area of very, very low concentration. But the thing that's different here is diffusion is not going through a small hole. Diffusion is going from an area of high concentration to low concentration. Effusion will be when we escape, it escapes from a small hole into an area of very low concentration or a vacuum. So we have Graham's law of effusion, and we can actually compare how quickly two different gases are going to effuse as long as they are at the same temperature. Okay, so we can find the rates or the ratio of the rates of the effusion by using their molar masses. So we have the rate at which gas A effuses versus the rate at which gas B effuses, and we can again relate that to their molar mass. I will have you look over here and see that these are opposite, right? This is B over A and this is A over B. Usually, the way that we will define this is that we will have A as being our lighter gas, our gas that will effuse more quickly, and B will be our heavier gas, which will then effuse less quickly. This way, you're going to get a large number for your rate, like a large positive number for your rate, versus a larger value that you're going to get calculated on this other side. So this will make sense when I show it to you, I think. So this says, how much faster does hydrogen escape through a porous container than sulfur dioxide? So we can have our rate, actually we should have our equation on here. There we are. Our rate of hydrogen versus our rate of sulfur dioxide. So like I said, I will usually make our lighter gas, gas A, and our heavier gas, gas B, just so that we get larger numbers and we're not getting decimal numbers and we're having to invert them and all kinds of things. So then we need our molar masses. So our molar mass of gas B is going to be 64.06 because I said that was going to be our sulfur dioxide, and this will be grams per mole. And then our molar mass of hydrogen is 2.02 grams per mole. And so as you can see, when we divide these up, our units are going to cancel and we're going to be left unitless. And so we're going to get out of this, we will get 5.63. And essentially what that means is that hydrogen effuses 5.63 times faster than sulfur dioxide. And this makes sense, right? Hydrogen is a much smaller molecule. And so it will move more quickly, and when it's moving more quickly, it has a greater ability to effuse, right? Because it's going to have more opportunities to escape through that small container. So hydrogen will effuse 5.63 times faster than sulfur dioxide. Again, if we had these, like say we had switched these, you're going to get a decimal number. And if you ever get a decimal number, I would just then, flip this rate upside down that you're trying to talk about and do 1 over your decimal number to get it back to being, a larger number like this 5.63. Here's another application. If the density of hydrogen is 0.090 grams per liter and its rate of effusion is 6 times that of an unknown gas, what is the density of an unknown gas? And assume STP conditions. Okay, so we know this Graham's law of effusion here. We also know we have a formula for density, and especially density at STP. We know that density at STP is going to equal the molar mass over 22.4. So those together, we can, do something with this, because you'll see out of this rate equation, right, we can get a molar mass, and then we can plug that in to our density equation and get our density. So it says if the density of hydrogen is 0.90 grams per liter and its rate of effusion, that's what we're looking for. Its rate of effusion is 6 times that of an unknown gas. So our rate of gas A versus B is going to be 6. I'm going to say that hydrogen is probably going to be our gas A because hydrogen has a molar mass of 2.02 grams per mole. And you can't have anything smaller than that, right? There's no masses that are going to be smaller than that. So hydrogen is going to be our gas A, and so we're going to solve for the molar mass of gas B. So our rate of hydrogen versus our gas B is 6:1 because hydrogen effuses 6 times faster than our unknown gas. So that's going to be 6:1, or just 6, is going to equal the square root of our molar mass of our unknown gas versus 2.02 grams per mole of our hydrogen. So now we can go ahead and solve for our unknown gas here. We'll, square both sides. That will get us 36 is equal to our molar mass over 2.02 grams per mole. And we'll end up getting that our molar mass is 73 grams per mole. Okay, so now that we've got that, we're not done with our problem yet. It says if the density of hydrogen is 0.90 grams per liter and its rate of diffusion is 6 times that of an unknown gas, what is the density of our unknown gas? Okay, so we have our molar mass. Now we can plug it into our density equation. So we can say that density is equal to 73 grams per mole over 22.4 grams per liter. Those grams are going to cancel out. And then we are going to get, this is liters per mole, my apologies. Those moles are going to cancel out, and we are going to get that this is 3.3 grams per liter. Okay, so our unknown gas is actually a lot more dense than our hydrogen. We can actually go through and find out how much more dense if we were to compare them. So if we said, okay, our unknown gas is 3.3 grams per liter, and our hydrogen is 0.090 grams per liter, if we divide those up, we will get 37. So our unknown gas is 37 times more dense than our hydrogen, which is very, very dense. So, but out of this, we got our density of our unknown gas, 3.3 grams per liter. So we can combine what we've learned already about gases before with now our new problems using this Graham's law of effusion. Okay, our last topic for today is ideal versus real gases. So thus far in this class, we've talked about ideal gases. And so that's why we used the kinetic molecular theory, right? We said essentially we're going to treat the gas particles as if they have a 0 volume, and we're going to treat them like they are not attracted to each other, right? That the gas particles just fly past each other and are not attracted to each other whatsoever. But in reality, these gas particles do have some volume and they are attracted to each other a little bit. And so this becomes an issue at high pressure and low temperature. Okay? The real gases will no longer behave like ideal gases at those conditions. So we need to have an equation to account for this change in behavior. Okay? And so I'll show you that equation in just a little bit. So like I said, our ideal gas laws assume that there were no attractions between the gas molecules and that the gas molecules do not take up any space. But like I said, in reality they do, and at low temperatures and high pressures, these assumptions are not valid. So if you look, right, our molar volume of our ideal gas is 22.41 liters, right? That's that 22.4 we keep using. But if we look at, let's say chlorine. Well, chlorine is not 22.4 at STP. It's close-ish, right? But it's not 22.4, and neither is carbon dioxide, right? It's not 22.4. The smaller the gas particles are, like hydrogen and helium, the more they are going to behave like ideal gases because those particles are not going to take up any space. Also, hydrogen and helium are nonpolar gases, if you've learned about polarity in previous chemistry classes. And so if they are nonpolar gases, they are going to be less attracted to the other gas molecules. So if we have a very small, very nonpolar gas, like hydrogen or helium, they're going to behave the most like an ideal gas. But as soon as we get into larger gas particles, on the molar mass, or just larger in general, And if they have some kind of polarity, then they are going to behave less like an ideal gas. So at very, very high pressure, as we increase and increase and increase the pressure, we start to see this deviation here, right? Where our gases stop behaving like ideal gases. So at a high pressure, our volume is actually going to be higher than we would predict because those real gas molecules are actually taking up space, right? So at high pressures, we are compressing the gas molecules. We are squishing them closer together, right? We're making the volume smaller and smaller and smaller. And as we make that volume smaller and smaller and smaller, right, that means that we are needing to take into account the volume of the particles themselves because there's not a very large volume altogether. So the smaller our volume is, the more the volume of those individual gas particles matter. Okay, so as we increase the pressure, we're going to have a deviation in the volume. That volume will be higher than we expect. As we decrease the temperature, we are also seeing a deviation. And so this one has to do with the attraction. Those real molecules are actually attracted to each other. Even if they're nonpolar, they'll still have London dispersion forces that are attracting them to the other gas molecules. And so as we decrease the temperature, we're getting those attractions. So our pressure due to the gases is actually going to be lower because the gas particles are attracted to each other, so they're not hitting the wall of the container as frequently. They're kind of lingering next to the other gas particles. So this is going to be even more important at very low temperatures because the gas particles aren't moving as quickly. So as they're moving more slowly, they're lingering, right? And so they're experiencing more attraction to the other gas particles, which is causing a decrease in the pressure. So here we're affecting the volume, right? On this last slide, the volume is going to be affected at high pressure, and the pressure is going to be affected at low temperature. So we have an equation that accounts for these changes because in the real world, sometimes it's important to take these changes in conditions into account. Sometimes it's not, but if we're working kind of at room temperature conditions, maybe it's not as important. But if you're working under very high pressures or very low temperatures, this could be a big game changer. So we have this van der Waals equation that will combine all of these different pieces that we've talked about before, and it will account for molecular volume, it will account for the intermolecular attractions, and it will correct for them. So this is what we use for real gases. So we have, and I know it looks like a mess, I'll explain it. In this, we have essentially PV equals nRT. This is P. This is V, and we have it still equal to nRT, which is great, right? And so this is based on our ideal gas law. But again, because we're not working with ideal gases, we have some corrections in here. So this A times N over V squared, that is going to correct our pressure for those intermolecular forces. And that that NB right here will correct for the volume of the actual gas particles. So we're still using this ideal gas law, we just now have some corrections so that it will account for all of these other conditions. And again, this would be important at very high pressures and very low temperatures. I do want to note that you are not responsible for memorizing this van der Waals equation. If you need it on a quiz or a test, I will provide it for you. You do not need to memorize this. In addition, you don't need to memorize the constants for the gases. You just need to be able to use those constants in this equation and explain, why we might need this equation. So here's our example. It says calculate the pressure exerted by 0.3 moles of helium in a 0.2 liter container at negative 25 degrees C using the ideal gas law and the van der Waals equation. And in this way, we can see the difference, right? So the first one we would do PV equals nRT. So it says calculate the pressure. So we are going to rearrange for pressure. We have pressure is equal to nRT over V. So we can plug in all of our values. We get, 0.3000 moles times our R value, 0.08206 liters atmospheres over moles Kelvin, times our temperature in Kelvin. So we're going to add 273 to 25 and we'll get 248 Kelvin. And we'll divide this all by our volume, which is 0.2000 liters. And out of this, we will get that our pressure is equal to 30.5 atms. And that would be if this gas behaved ideally, okay? But, now we're going to go ahead and calculate it using the van der Waals equation. And so the van der Waals equation is P plus A times N over V squared. And so that's our pressure. And then that gets multiplied by our volume, V minus NB, and that's all going to be equal to nRT. Okay, so I'm going to go ahead. I looked at the values from the previous slide. So we needed our values for A and B, right? So we had, and we're working with helium here. So A is going to be 0.0342 and B is going to be 0.02370. Okay, so our P is what we're trying to solve for. We have our A value of 0.0342. Our N is going to be our number of moles, so 0.3000. And here I'm leaving out units just because it's going to get a little bit messy and I will run out of room. You can feel free to include them. I just don't have room on this particular slide. So we've got that squared times our 0.2000 minus our N value times our B value. And that's going to equal nRT. So I'm going to run out of room here. So there's N times R times T. Okay, so now if we start, multiplying this and simplifying this, eventually we are going to get P plus 0.0770 times, once we simplify all of that, we're going to get 0.1929, and our right-hand side is going to equal 6.11. So we can further rearrange. So we're going to get P plus 0.0770 is equal to 31.7. So we'll get that P is equal to 31.6 atms. Okay, so now if we compare these two things, right, we have our pressure from the ideal gas law was 30.5 atms, and our pressure using the van der Waals equation is 31.6 atms. Okay, so there is, a decent difference here, and it's not even that cold, right? Negative 25 degrees C, but we are seeing a significant difference here. So sometimes it will matter, and if you're going to, be working with gases, it's a good idea to use the ideal gas law, the van der Waals equation to make sure that your calculations are as accurate as possible. Our ideal gas law works for a lot of situations, but like I said, if you're going to do things that are very precise, the van der Waals equation is going to be a better option because it's going to give you more accurate data because you're not taking into account all of these assumptions about the volume of the molecules and the interactions between the molecules. Okay. That is the end of our lecture on gases. So make sure you're doing all of those Chapter 5 lecture worksheet problems. Keep working on them. If you have any questions, please send them my way, and I will see you guys next time when we start Chapter 6.